Because we can't afford the time it would take to move molecules over long distances to send signals, neurons instead use electrical signaling in the form of propagating action potentials. Now, while action potentials are clearly an electrical phenomenon, the propagation of an action potential is quite different from the transmission of a signal down a telephone cord or an Ethernet cable. In a wire, say in an electronic device or in an old-fashioned telephone, signals are conducted down the wire. The wires in electrical devices are made up of low-resistance materials, like copper. Lower resistance means lower voltage drops from one end to the other. Over short distances, this voltage drop is no big deal, but over longer distances it can be a deal-breaker, requiring large voltages to transmit signals. The nervous system must be able to send signals over fairly large distances, and nature doesn't have the luxury of using a material as conductive as copper. The conductivity of cytoplasm is about 10 million times less than that of copper. In an axon, the losses over distances are even greater because of the leakage of current out of the cell and capacitive effects across the membrane. So we can't just fire an action potential with an amplitude of around 100 millivolts, the cell body, and expect it to propagate all the way to the end of a meter-long axon. So we have two options. First, we could increase the amplitude of the action potential to be much larger, so the signal gets there in spite of the resistive and capacitive losses. However, at around negative 70 millivolts resting potential, neurons are already almost at their breaking point. 70 millivolts isn't a huge voltage, but the membrane is only a few nanometers thick. This means that there's a huge electric field across the membrane itself, around 10 million volts per meter. Even at its ordinary resting potential, the membrane isn't far off from its so-called breakdown voltage, the voltage at which the lipid bilayer stops acting as an insulator. So raising the membrane potential isn't an option. The other option is the one that nature takes. We must repeatedly regenerate our signal to get it down the axon. The result is a situation where rather than moving a molecule down the axon, or moving electrons down a wire, we instead move the state of depolarization down the axon.